Welcome to Daily Papers, the podcast where we break down the latest and greatest research into bite-sized pieces. Today, we're talking about a paper that could fundamentally change who gets to build powerful AI.
That's right. Right now, if you want to train a massive frontier-level AI model, like the ones that power the best chatbots, you need one thing: a data center. A massive, purpose-built, jaw-droppingly expensive data center filled with tens of thousands of identical, top-of-the-line GPUs.
And who has those? A handful of very, very large tech companies. It's created a kind of walled garden where only a few players can afford to innovate at the cutting edge. Meanwhile, there's this enormous, untapped pool of computing power sitting in millions of gaming PCs and workstations all around the world.
Exactly. And this paper, titled Agora, Collective and Permissionless Internet-Scale Pre-Training of Large Language Models, asks a really powerful question. What if we could harness all of that distributed power? What if we could train a giant AI model using thousands of regular computers owned by different people, all cooperating over the regular internet?
It sounds amazing, but also kind of impossible. Training an AI is like conducting a symphony orchestra. You need all the musicians in the same room using professional instruments connected by the low-latency network of, well, air, all following a single conductor in perfect time.
And trying to do it over the internet is like trying to conduct that symphony over 1,000 loggy video calls. Some people have great internet, some have terrible internet. Some people's computers might crash. Someone might just decide to go and make a sandwich mid-performance. It's chaos.
So how did these researchers from a group called Pluralis Research manage this chaotic internet orchestra? They built a system they call Agora, named after the public meeting places of ancient Greece, and it's built on a few really clever ideas to handle the chaos.
The first big idea is how they deal with the model itself. A huge AI model is too big to fit on one person's computer, so they use something called pipeline parallelism. Think of it like a car assembly line. The model is broken into stages, and each computer, or worker, is only responsible for one small part of that assembly line.
Okay, so I'm in charge of putting the doors on, and you're next in line, and you put the wheels on. But over the internet, shipping the half-built car between us after every single step would be incredibly slow. That's the communication bottleneck.
Exactly, and this is Agora's first magic trick. They figured out a way to massively compress the information passed between stages by a factor of 100. So instead of shipping a whole car, it's like you're just sending me a tiny, super efficient blueprint of the changes you made. It's a technique called reparameterized subspace networks, but the point is, it makes communication over slow internet links possible.
Okay, so that's how the assembly line works. But to make it faster, you want multiple people working on the same stage. Let's say we have 4 people all working on door installation. How do you make sure they all stay in sync and don't end up with 4 slightly different versions of the car doors?
This is the second problem. Traditionally, every time the model learns something new, all the computers have to stop, share their updates, and wait for everyone to agree. It's a synchronous process. Over the internet, you'd be waiting forever for the slowest person.
The orchestra stopping after every single note to make sure they all played it correctly.
Precisely. So Agora does something completely different. Asynchronous sparse weight averaging. Let's break that down. Asynchronous means you don't wait for anyone. You just keep working and share your updates in the background.
Okay, no more stopping. What about sparse?
Sparse means you don't even share all of your updates. You just share a small random fraction of them each time, say 5%. And finally, weight averaging means you're averaging the model's underlying knowledge, its weights, which change very slowly, not the immediate, noisy updates.
So instead of stopping after every note, the musicians just keep playing, and every so often they casually listen to what a few of their colleagues are doing and slightly adjust their own tuning. It's not perfect, but it keeps everyone roughly in tune without ever stopping the music. I love that analogy. It handles the slowness of the internet. But what about the unreliability? What happens when my computer crashes or I get bored and turn off my PC?
The system is designed for it. This is what the paper calls churn. people constantly joining and leaving. In Agora, there are lightweight processes called trainers that act as the conductors handing out work. If a computer or worker suddenly goes offline, the trainer just shrugs and sends the next piece of work to someone who is online. No single person is critical. The system is elastic and just routes around failures.
So this all sounds incredible in theory, but the big question is, did it actually work?
It absolutely did. This wasn't just a simulation. They conducted a public permissionless training of an 8.6 billion parameter model they call Pluralis 8b. Over 40 days, 330 different contributors from around the world joined with their own hardware, mostly high-end consumer GPUs.
And the results? The model trained successfully. It converged, meaning it actually learned, and they measured its efficiency against a baseline of training a similar model in a state-of-the-art data center. Agora achieved about 63% of the efficiency.
That sounds incredibly good, considering it was running on a hodgepodge of consumer hardware connected by janky home internet connections.
It's amazing. It proves the principle is sound, and the implications are huge. This is a path toward democratizing AI development. They call it the paradigm of protocol learning, where training is a protocol anyone can join, not a process locked inside a corporate data center.
And one of the coolest side effects is that because the model is split into pieces across all these different participants, no single person ever possesses the full, complete model. It's a collectively trained and collectively owned asset.
It really is a paradigm shift, moving from a world where only a few giants can build frontier AI to one where a global community can collaborate to do the same. That's all we have time for today on Daily Papers.